Well, hello there. Today we're going to be talking about stringed and piped instruments. Things that we're going to learn. Why wavelength is related to the ends of an instrument, and how to calculate the wavelength and frequencies an instrument can produce. Stringed instruments. Well, what I want to start off right away is saying that the wavelength is 2 times the string length. And there's a specific reason for that. Let's say that we had a guitar, for example. There's my example of a guitar. I'm just going to put 1 string on here. Down here we've got our fret, and down here it's locked into place. Well, what I want you to notice here is down here, this would be what we'd call a node. There's not going to be any movement. And right here is another node. In the center would be an antinode. So if you think about this string, right, the first string, the longest wavelength, is going to be like this. And if we continue it, we find out that it's going to be twice as long, because this is half of the wave and here's the other half of the wave. So a wavelength is going to be 2 times the string length. And there's a couple wavelengths that we'll go through here. The first one is half a wavelength, because we have to ask ourselves, where are the nodes? Now we can move this back on the guitar so that we have, well, there's a lot of stuff I'd have to erase there. Let's erase as much of this as I can. Alright, let's draw the guitar back in there again. Guitar looks a little bit more like an electric guitar this time, but that's alright. Now, we can use a different color line. We can move it back, but we have to keep in mind that the end pieces are going to be nodes. Where would the next node be? For example, I can't very well likely put a wave in here like this, because my end piece, I'm at an antinode, and I have to be here at a node, because that's just the way a guitar is. So I can put 1 complete wavelength in here, and that's where we get the string length is equal to 1 wavelength. Likewise, I can keep smashing this back, and I can get 1.5 wavelengths in here. If I can draw it exactly, but there's 1, and then there's 1.5 wavelengths. So here's the first one, and then here's half of another one. So it's 3 halves of a wavelength. The last one, as you can imagine, is just getting 2 wavelengths in there. But the important thing is that I'm finishing, there's 1 wavelength, and I have to finish at a node. And I have to start at a node for these strings. Hopefully that makes some sense to you. Well, in here they say, what is the fundamental frequency sounded by a violin string 45 centimeters long? Right away, the fundamental frequency is the first wavelength, and that would be simply taking the length of the string and doubling it. So my wavelength here, or we could say, start using the correct terminology here, lambda is 0.9 meters. Alright, they give us the wave speed to be 280 meters per second. Now I'm not quite ready to find the fundamental frequency, but I can find the period. And then I can just take the inverse of that. The period in this case turns out to be 0.003 seconds. And if I take the inverse of that, my frequency, which is what we're really wanting here, turns out to be 311 hertz. Alright, what are the wavelengths of the 4 longest waves that can stand in a string 60 centimeters long? Well, that just goes back to what we had earlier. right here are our 4 longest wavelengths. Notice the wavelength is getting smaller each time in this case. So I'm just going to simply use this equation and start to work my way down it. But I'm going to use these are my 4 longest, henceforth the reason I gave those to you. So in here, I know that I'm just going to use a little abbreviation. String length equals half of the wavelength, sorry. And let's not use WL, let's continue to try to start using the right terminology here. Half of lambda. So in this case, my string length is going to be 60 equals half of the wavelength. So my one wavelength would be 120. In the next case, it's 60 equals 2 over 2 wavelengths, or just one wavelength. So it would be 60 centimeters. And then 60 equals 3/2 the wavelength, so I multiply by 2 and divide by 3, and I get lambda equals 40 centimeters. And then in the last case, it's 60 equals 2 wavelengths, or my lambda wavelength is equal to 30 centimeters. Well, now that we've done this, this is what are the 4 lowest frequencies of a 60 centimeter string if the speed of the wave is 240 meters per second. Well, that's what we found. The longer the wavelength, the lower the sound, the lower the frequency. So I can find the period for each of these and then go back and find that frequency. So I'm going to do one example and let you guys do the other 3. The first example, alright, is going to be distance. Wavelength equals velocity times period. So my first one's going to be 120 equals the velocity of 240 times the period. Well, I can look at this and say my period is 0.5 seconds. Oh, I did something wrong here. It's really not 120, it's 1.2 meters. It's 120 centimeters. So it's going to be a 1.2 divided by 2. Alright, when I divide this out, I'm going to get 0.005 seconds, and then the frequency is just going to be the inverse of that, which means my frequency turns out to be 200 hertz. Well, I've done the first one. You can do the next 3 because I found the first of the 4. Remember, this right here is going to be 0.6 meters, 0.4 meters, and 0.3 meters. Use our distance equation, solve for the period, solve for the frequency. Okay, pipes. Pipes that are closed on one end. Pipes that are open on both ends would be exactly the same, except they have to be antinodes on both sides instead of antinodes. So they're going to follow the exact same format that's stringed if the pipes are open on both sides. But if we have a pipe that's closed on one end, such as this, for example, and we have this wave that comes emanating out of it. Right. Well, what we find out here is that the first wave, in this case, I'm not drawing a very good picture of it here, in this, it would actually be at a antinode right here. And if I were to shrink this, this is actually to the first antinode, that's only 1/4 of the way through. Right, 1, 2, 3, 4 parts of a wave. So we say the pipe length, the first one, is 1/4. Now if I were to shrink this down to the next wavelength again, right, so until I get to the next antinode, which is going to have to be here. Notice that is 1, 2, 3/4 of a wavelength. And that would take me to here, where I'm back to an antinode again. And then I could shrink that again till I get to the next antinode, which should be right here, would be the 5/4. That would take me to the next note. And I could put it in there and redraw it and shrink it down, but that would be the next antinode. And it keeps going by this as we go through here. So I hope you've learned some from this. Remember, it all deals with, are we starting with a node or an antinode, and are we finishing with a node or an antinode? Hey, I'll see you on the flip side.